3 is not in my common for all four equations shaded area. It is, however, one of the possible solutions to the sloped line. But because what they had in common for the height of the y-axis is 2, the 0, 3 cannot be a solution. We're going to try to do some modeling of a real-life problem with dealing with linear inequalities. We're going to follow the same steps we did with the story problems when we were talking about equations. We want to go through and see if we can find the information and if that information can give us any results that are possibly constant terms. So the details that we see here are going to be that we need at least 3 medium throws. So that's an inequality statement right there. The number of medium throws have to be greater than or equal to 3. Again, these are inequalities, so you're looking for those keywords like least or at the most. We have another least here. We need at least one of the long throws. So the number of long throws also makes an inequality statement of greater than or equal to 1. Now we could then assign each of these a variable, our x and our y. These are going to give us our horizontal and vertical boundaries. Now, the last thing that we find out is the minimum order for free delivery. Now, because it says minimum order, that's the smallest the order can be. It can be even larger than this, but it has to be at least 10,000. So again, another way to say the words at least. So it has to be greater than or equal to the 10,000. They want to know how many or what the combination is of the medium and the long throw spotlights in order to achieve that free delivery. So we would get that by number of the medium throws has to be at least 3, and then the price of those medium throws, and the medium throws are going to be 1,000. So we have a variable here, and we have a constant, which then becomes a coefficient. We also have, we don't know how many of the long throws we're going to get, but that's going to be y, and that y is going to then be multiplied by the 3,500. The reason I filled in this equation, inequality statement, is because then we could go back and we could test some other possibilities. Now, because we have the 3 combinations, we need to follow the certain amount of medium throws, the certain amount of long throws, and try to figure out what is the largest number of those we can get to still qualify for the free shipping of an order of $10,000 or more. We have 3 different equations that we can graph. The graph of the systems of the inequalities is shown. Any point in the shaded region, again, of the graph is a solution of the system. So another thing to point out is we would not order a fraction of a spotlight. So we're going to look for actual intersecting points on our grid. We don't want parts that would not go to a full value. So we're going to ask now, what about would the 0.41 work? That's representing, could we buy 4 medium throw spotlights? We needed at least 3, so we've covered that requirement. And 1 long throw, we need at least 1, so that requirement is also being covered. Now we have to see when we graph those 2 inequalities, does that graphed point, that coordinate point, fall within our solution area? And it does not. So the delivery would only be free in the shaded area. Showing that with the equations, we could go to the next question. What if we bought 5 medium throws, again, satisfying it had to be at least 3, and 2 long throws, satisfying it had to be at least 1? Would our delivery be free then? So for this one, To check it simply on a graph, if we had a graph already, we would go to 5, 2. 5, 2 is on or is contained in our shaded area, so that would be a solution. To prove that that is true, I went ahead and I substituted it in for our combined inequality statement, and it is true that that combination of medium and long throws would equal up to 12,000, and our order needed to be at least 10,000. So a couple other ones that are not contained in the textbook. What is the greatest amount as shown on the graph? So that means it would be just the solutions from 3, because we had to have at least 3 of them, up to 10, because that's what our graph is showing the results of. Of medium throws, combined with the least amount of long throws, which they told me I needed at least 1, will qualify for free shipping. So we're going to go to, we need 3 mediums, and we need at least 1. We could not get the 3, 1, but if we ordered 3, 2, could we get that? So 3, 2, I plot that point, and because the equal sign, or equal to, is part of the inequality symbol, it can lie right on the lines, so 3, 2 would be the smallest order that I would be able to make. That would be the least expensive order. Again, I could then place the 3 and the 2 in here. 3 times 1,000 would result in 3,000 plus 7,000, and yes, we've got our smallest order because it equals $10,000. Then I checked to see what is the minimal amount of long throws if I only buy the minimal amount needed of the mediums. So I needed only 3, and this would be the minimal amount I could buy here. Now, if I had no budget, I could go with 3 mediums, and I could buy an infinite amount of the long throws. The same would hold true if I had no budget. I could buy, if I look here, I could buy 3 would be my minimal, but anything above 7 I could also buy. Because if I bought 7, 1, that's going to be that largest or that smallest combination. If money was no object, we could continue to buy more and more of the medium ones because we have satisfied our at least one of the long ones. This then concludes the lesson on systems of linear equations and inequalities we dealt with.